What if everything you thought you knew about reality was just the surface of something far more bizarre and mind-bending? Picture this: time bending and stretching like a rubber band, invisible forces shaping the entire universe, and regions of space where the rules of physics as we know them completely break down. Welcome to the mysteries of spacetime, the ultimate fabric that weaves together our existence. In this video, we're diving into 20 astonishing facts about spacetime that will leave you questioning everything you know about reality. From the curious behavior of time near black holes to the ongoing enigma of dark energy driving the universe's expansion, we're unraveling the secrets that even the greatest minds in science are still grappling with. So get ready, because what you're about to discover will change the way you see the universe forever. Now, turning to the very foundation of our journey, let's explore the concept of spacetime itself. This groundbreaking idea owes its origins to Albert Einstein and his revolutionary theory of relativity. Before Einstein, space and time were considered separate, almost like independent backdrops against which events played out. But his work merged them into a single entity, a four-dimensional continuum we now call spacetime. Imagine it as an intricate fabric where three dimensions of space, length, width, and height, are woven seamlessly with the fourth dimension, time. This unification was not just a mathematical tweak, it redefined our understanding of reality. Spacetime is not static. It can stretch, warp, and bend under the influence of gravity and energy. This insight replaced the centuries-old notion of gravity as merely a pulling force, revealing instead that it is the curvature of spacetime itself that guides the motion of stars, planets, and even light. This paradigm shift opened the door to understanding phenomena like black holes and the expansion of the universe, fundamentally altering how we perceive the cosmos. From this concept, everything else about spacetime springs into existence, forming the stage upon which the grand drama of the universe unfolds. Moving forward, let's uncover a truly mind-bending aspect of spacetime. Time itself does not flow equally everywhere. This phenomenon, known as time dilation, reveals that the ticking of a clock can speed up or slow down depending on factors like gravity and motion. At the heart of this concept is Einstein's theory of relativity, which shows that time moves more slowly when you are closer to a massive object like a planet or a star due to the intense gravitational pull. Similarly, time also slows down for objects moving at very high speeds. To bring this closer to daily life, let's consider GPS satellites orbiting Earth. Positioned thousands of kilometers above us, these satellites are farther from the planet's gravitational field compared to clocks on the ground, meaning time ticks slightly faster for them. Scientists must correct these time differences to ensure GPS systems work accurately, allowing us to find directions on our phones or track global navigation. Imagine how intricate and precise this must be. Subtle differences in time impacting technology we rely on every single day. This seemingly strange aspect of spacetime is not just theoretical, it has real consequences for how we interact with the world. Time running differently at various points might feel like science fiction, but it is a fundamental reality shaping everything from our daily routines to the grand structure of the cosmos. Moving forward, let's delve into another astonishing aspect of spacetime, its ability to bend and curve. This curvature is the very essence of what we experience as gravity. Imagine spacetime as a gigantic, flexible rubber sheet stretched out flat. Now, place a heavy ball in the center of this sheet. The ball sinks into the sheet, creating a noticeable curve. If you were to roll a smaller ball across the surface, it would naturally move toward the heavier ball, not because they are directly pulling on each other, but because the smaller ball is following the curve created by the larger one. This is a simplified way of understanding how massive objects like planets, stars, and black holes warp the fabric of spacetime. The greater the mass of an object, the deeper the curve it creates, and the stronger the gravitational pull you feel. This concept was revolutionary, introduced by Einstein's general theory of relativity, changing the way we understand gravity. It is not a force pulling objects together, as once thought, but rather the result of curved spacetime guiding the motion of objects. For example, the Earth orbits around the Sun because the Sun's immense mass creates a deep curve in spacetime, and Earth is essentially rolling along this curve. Even light, traveling at incredible speeds, bends when it passes near extremely massive objects, a phenomenon proven during a solar eclipse when starlight was observed bending around the Sun. Understanding spacetime as a dynamic, flexible entity reshaped by mass and energy gives us a profound insight into how the universe operates on its grandest scales. Now turning to black holes, they represent the most extreme examples of spacetime curvature in the universe. Picture a stellar object so massive and dense that it collapses under its own gravity, warping spacetime to an unimaginable degree. At the heart of a black hole lies what is known as a singularity, a point where the density becomes infinite and our current understanding of physics begins to break down. Surrounding this singularity is the event horizon, often described as the point of no return. Once anything crosses this boundary, whether it is light, matter, or even information, it is irretrievably pulled into the black hole's depths. Time itself behaves in bizarre ways near a black hole. For an observer watching from a safe distance, anything falling toward the event horizon appears to slow down, as if frozen in time, never fully crossing the boundary. This effect, called time dilation, occurs because the immense gravitational pull of the black hole drastically stretches spacetime. For someone theoretically plunging into the black hole, however, time would seem to pass normally from their perspective, while the rest of the universe appears to speed up. It is a strange, almost paradoxical phenomenon that underscores the mind-bending effects of spacetime near such gravitational giants. Black holes do not just warp space and time, they also twist our understanding of reality. Scientists continue to study these mysterious objects to uncover their secrets, pushing the boundaries of physics and giving us a glimpse into the enigmatic workings of the cosmos. With this captivating concept in mind, let us journey further into the wonders that spacetime reveals. Moving forward, let us explore the fascinating concept of wormholes, scientifically known as Einstein-Rosen bridges. These theoretical constructs are imagined as shortcuts or tunnels through spacetime, potentially connecting distant points in the universe. Picture spacetime as a sheet of fabric. If you fold it so that 2 points touch, a wormhole would be the bridge that connects those points, allowing for an almost instantaneous journey between them. This idea has captured the imagination of both scientists and storytellers for decades, becoming a staple in science fiction. In countless books and movies, wormholes serve as convenient portals for interstellar travel, enabling characters to cross vast cosmic distances in the blink of an eye. But what does science have to say about their existence? In theory, wormholes could exist within the framework of general relativity, but there is a catch. For a wormhole to remain stable and traversable, it would require an exotic form of matter with negative energy to keep it from collapsing. Unfortunately, this exotic matter has never been observed, and its existence remains purely hypothetical. Furthermore, even if such a wormhole could exist, it might be microscopic in size, far too small for any practical use. Even more puzzling, some models suggest that attempting to pass through a wormhole could cause it to collapse instantly, trapping anything inside. This makes the reality of using wormholes for travel incredibly complex, if not impossible, given our current understanding of physics. Despite these challenges, the very idea of wormholes fuels some of the most cutting-edge research in theoretical physics. They raise profound questions about the nature of spacetime and the possibilities of connecting distant regions of the cosmos, or perhaps even different universes altogether. While no evidence has yet been found to prove their existence, wormholes remain a tantalizing possibility, inviting us to dream about what might lie on the other side of spacetime's mysterious fabric. As we continue this journey through the marvels of spacetime, let us turn to another fundamental idea that shapes our understanding of the universe. Now turning to the speed of light, one of the most fundamental constants in the universe, let us delve into its profound connection with spacetime. Light travels through the vacuum of space at an astonishing rate of 300,000 kilometers per second. This speed is not just incredibly fast, it also represents the ultimate speed limit of the cosmos. According to Einstein's theory of relativity, nothing can travel faster than light. But why is this so? The answer lies in the very fabric of spacetime itself. At its core, spacetime is structured in a way that imposes this universal speed limit. When an object moves faster, its mass effectively increases, and so does the amount of energy needed to accelerate it further. As an object approaches the speed of light, its mass grows without bounds, requiring infinite energy to reach that ultimate speed, a practical impossibility given the laws of physics as we understand them. This limit not only governs how objects move, but also how information and even causality are preserved throughout the universe. Imagine light as the messenger carrying information across the universe. If anything could travel faster than light, it would distort the very sequence of cause and effect, breaking the fundamental order of events in spacetime. Moreover, this cosmic speed limit is deeply tied to the concept of time dilation, where time slows down for objects moving close to the speed of light. For example, astronauts aboard high-speed spacecraft would experience time differently than people on Earth if they could approach anything near this extraordinary velocity. This interplay between speed, time, and energy is a testament to the intricate design of spacetime. The speed of light is not just a number, it's a boundary that defines the behavior of the universe and underpins all of its physical laws. With this understanding in hand, we can see how the speed of light governs the structure of spacetime and restricts the possibilities of travel and communication across cosmic distances. As we move ahead, let us explore how these same laws of physics reveal another surprising truth, one that involves the ever-expanding nature of the universe itself. Moving forward, let us uncover one of the most remarkable aspects of spacetime, the phenomenon of its expansion. At first glance, it might seem like the galaxies in the universe are simply moving away from each other, as if they were flung outward by some ancient cosmic explosion. But the reality is far more intriguing. It is not just the galaxies that are in motion, spacetime itself is expanding. Imagine the universe as a giant balloon with galaxies painted on its surface. As the balloon inflates, the distance between each galaxy increases, not because the galaxies themselves are moving, but because the fabric of spacetime is stretching. This profound discovery was first made by the astronomer Edwin Hubble in the early 20th century, who noticed that the farther a galaxy is from us, the faster it appears to be receding. The driving force behind this expansion is something scientists call the cosmological constant, first introduced by Albert Einstein. The cosmological constant represents a mysterious form of energy inherent to spacetime, often referred to as dark energy. This energy acts as a repulsive force, countering the pull of gravity and causing the universe to expand at an accelerating rate. Without this phenomenon, the universe might have stopped expanding long ago or even collapsed back into itself. Dark energy, though making up nearly 70% of the universe, remains one of its greatest mysteries. Scientists have yet to determine its true nature, but its effects are undeniable. It is the silent architect of the ever-growing cosmos, gradually pushing galaxies farther and farther apart. What is even more mind-boggling is the implication of this accelerated expansion. Over astronomical timescales, the universe will appear increasingly empty as distant galaxies vanish from view, carried away by the relentless stretching of spacetime beyond the reach of even light itself. This expanding universe paints a dynamic and evolving picture of spacetime, one that continues to shape our understanding of the cosmos. As we marvel at this grand cosmic dance, let us take a closer look at how it all began with the birth of spacetime during the monumental event we call the Big Bang. Now turning to the origins of spacetime, we arrive at the monumental event that marked the beginning of everything, the Big Bang. Roughly 13.8 billion years ago, the universe as we know it began in a moment of incomprehensible density and heat. But here is where it gets truly fascinating. The Big Bang was not just an explosion of matter into empty space. Instead, it was the birth of spacetime itself. Before this event, there was no time, no space concepts that are difficult, if not impossible, to grasp within the confines of our everyday experiences. To imagine this, think of spacetime as a vast, ever-expanding canvas, and the Big Bang as the moment that canvas first unfurled. It was the instant when time began ticking and space began stretching. From that singular point of origin, all of existence began to expand outward. In its earliest moments, the universe underwent an incredibly rapid period of inflation, growing from subatomic scales to cosmic dimensions in a tiny fraction of a second. This inflation set the stage for the formation of the galaxies, stars, and planets we observe today. Imagine the universe as a bubbling pot of energy, where fluctuations and ripples eventually seeded the structures of the cosmos. These ripples, captured in the faint glow of the cosmic microwave background radiation we observe even now, serve as a snapshot of the universe in its infancy and give us critical insights into how spacetime itself evolved. What makes this concept even more remarkable is that the Big Bang was not a conventional explosion, but rather the simultaneous emergence of space and time everywhere at once. The idea of asking what existed before the Big Bang is like asking what is north of the North Pole. It is a question without context, as time simply did not exist prior to this event. The Big Bang represents the ultimate boundary, the beginning of the timeline, beyond which our understanding and possibly the very fabric of reality ceases to apply. As we reflect on this incredible genesis of spacetime, let us venture even deeper into the mysteries it holds, exploring the theoretical possibilities of time travel and its implications in the next astonishing fact. Moving forward, we dive into one of the most captivating concepts born from the study of spacetime time travel. While it remains a staple of science fiction, theoretical physics does allow for the possibility of time travel under specific, albeit highly complex circumstances. The groundwork for this idea is rooted in Albert Einstein's general theory of relativity, which describes how massive objects warp spacetime. One intriguing solution within this framework is the concept of closed time-like curves. These are paths through spacetime that loop back on themselves, theoretically allowing someone to travel back to an earlier point in time. Imagine it as a cosmic shortcut that bends the arrow of time into a circle, seemingly bridging past and present. However, the challenges are as monumental as the concept is exciting. Creating such a loop in spacetime would require unimaginable amounts of energy and conditions far beyond anything achievable with current technology. Additionally, the introduction of time travel invites a slew of paradoxes, such as the famous grandfather paradox. This is the idea that if you were to travel back in time and alter a past event, say, preventing your own grandfather from meeting your grandmother, you could potentially erase your own existence. These dilemmas push the boundaries of our understanding of logic and causality, raising profound questions about whether time travel is feasible within our reality. Despite these obstacles, certain models and theories continue to intrigue scientists. Wormholes, or theoretical tunnels connecting distant points in spacetime, have been suggested as potential pathways for time travel. While these ideas remain speculative, they highlight how the laws of physics could, in principle, allow for journeys through time under specific conditions. Yet, even if such travel were possible, maintaining stability and avoiding destructive feedback within these tunnels would present nearly insurmountable difficulties. Time travel challenges us to rethink the very nature of reality, causality, and even free will. It stands as a testament to the mysterious and uncharted dimensions of space-time waiting to be explored. And as these theoretical ideas push the limits of our imagination, they also pave the way for future discoveries. Now, let us take another leap forward and explore how the rotation of massive celestial objects can twist the very fabric of space-time itself in a phenomenon known as frame dragging. Now turning to the fascinating phenomenon of frame dragging, we uncover how the rotation of massive objects can actually twist the very fabric of space-time around them. This effect, predicted by Albert Einstein's general theory of relativity, reveals yet another mind-bending aspect of our universe. To put it simply, when a massive object like a planet or star spins, its rotation creates a kind of swirling motion in the surrounding space-time, much like a spinning spoon stirring a cup of coffee. This distortion subtly drags the paths of objects and even light that venture too close, altering their natural trajectories. Imagine space-time as a malleable sheet, with a rapidly rotating object warping and twisting it as it spins. One of the most compelling confirmations of this phenomenon came through an ambitious experiment called Gravity Probe B. Launched by NASA in 2004, this spacecraft carried highly precise gyroscopes to measure the tiny distortions in space-time caused by Earth's rotation. Over the course of its mission, it successfully detected the subtle frame dragging effect, showing that Earth rotation indeed twists space-time in exactly the way Einstein had predicted nearly a century earlier. This was a monumental achievement, offering experimental proof of a once purely theoretical idea, and deepening our understanding of how massive, spinning objects influence their cosmic surroundings. Frame dragging has profound implications for our perception of space and time. It not only validates the dynamic, flexible nature of space-time, but also opens the door to exploring more extreme environments, such as those near rapidly spinning black holes. In such extreme scenarios, the effects of frame dragging become far more pronounced, creating regions where space-time itself is dragged along at incredible speeds. These discoveries push our understanding of the universe to new heights, offering glimpses into the extraordinary and complex interplay between motion, gravity, and the structure of space-time. As we unravel these cosmic mysteries, let us now journey to even denser, more extreme regions of the universe and explore the mind-boggling distortions of space-time created by neutron stars. Moving forward to the astounding realm of neutron stars, we encounter some of the densest objects in the cosmos, compacting more mass than our Sun into a space barely spanning the size of a city. These celestial wonders are formed when massive stars exhaust their nuclear fuel and collapse under their own gravity, leaving behind a core so dense that a single teaspoon of its material would weigh billions of tons here on Earth. This extreme density creates space-time distortions of an unimaginable scale, bending and warping the fabric of the universe in ways that challenge our understanding of physics. Neutron stars also exhibit extraordinary magnetic fields, millions to billions of times stronger than any magnet we can create on Earth. These magnetic fields, combined with their rapid rotation, sometimes spinning hundreds of times per second, generate beams of radiation that sweep across space. When these beams point toward Earth, we observe them as pulsars, which are essentially cosmic lighthouses. Studying pulsars has provided scientists with invaluable insights into the nature of space-time in these intense regions, as their precise and predictable signals allow researchers to probe the behavior of matter, gravity, and even the properties of space-time itself. Near a neutron star, space-time is stretched and twisted to such extremes that time itself slows down relative to an observer far away. This time dilation, predicted by Einstein's theory of relativity, has been observed and measured, further confirming the remarkable interplay between gravity and time. The immense gravitational pull of neutron stars also affects the light escaping from their surfaces, shifting its color to red and demonstrating the influence of gravity on electromagnetic waves. These effects make neutron stars powerful cosmic laboratories where the fundamental laws of physics are tested under some of the most extreme conditions in the universe. The study of neutron stars and their effects on spacetime is not only unraveling the mysteries of gravity, but also providing clues about the universe's most enigmatic phenomena, such as black holes and even the potential existence of new states of matter. With each discovery, neutron stars reveal a glimpse into the awe-inspiring complexity of the cosmos. From these spinning beacons of light, let us now pivot to another cosmic mystery, the enigmatic force driving the accelerated expansion of spacetime itself, dark energy. Now turning to the mysterious force known as dark energy, we confront one of the most perplexing enigmas in modern physics. Dark energy is believed to make up about 68% of the universe, yet its true nature remains shrouded in mystery. It is the driving force behind the accelerated expansion of spacetime, a phenomenon first discovered in the late 1990s when astronomers observed distant supernovae and found that galaxies are not just moving apart but doing so at an ever-increasing rate. This revelation fundamentally changed our understanding of the cosmos, suggesting that some unknown energy is counteracting gravity on a cosmic scale. Dark energy is thought to work uniformly across spacetime, exerting a sort of negative pressure that pushes the universe to expand faster and faster. Unlike gravity, which pulls matter together, dark energy appears to have the opposite effect, making it a key factor in shaping the universe's ultimate fate. Despite its profound influence, scientists have yet to directly detect or measure dark energy. Its existence is inferred from its effects on the large-scale structure of the universe, such as the motion of galaxies and the patterns observed in the cosmic microwave background radiation. Several theories attempt to explain dark energy, but none provide a definitive answer. Some scientists propose that it is a fundamental property of spacetime itself, often linked to the cosmological constant introduced by Einstein in his theory of general relativity. Others suggest it could arise from an entirely new and unknown field, or that our understanding of gravity might require revision on cosmic scales. As we continue to explore this enigmatic phenomenon, dark energy not only challenges our comprehension of physics, but also underscores how much there is yet to learn about the universe. The study of dark energy raises profound questions about the origin, evolution, and destiny of the cosmos. Will the universe continue to expand forever, or could it eventually slow down due to other unknown forces? Each investigation into dark energy pushes the boundaries of science and inspires us to seek answers to some of the deepest mysteries of existence. And with that, let us now navigate toward another fascinating aspect of spacetime, the ancient signals left behind by the universe's earliest moments, encoded in the cosmic microwave background. With the next phase of the journey in sight, let us delve into the cosmic microwave background radiation, an extraordinary relic from the universe's earliest moments. Often referred to as the afterglow of the Big Bang, this faint radiation is a snapshot of the cosmos as it existed nearly 14 billion years ago, just 380,000 years after the Big Bang. At this point in history, the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely for the first time. This released light has been traveling across the universe ever since, stretched by the expansion of spacetime into the faint microwave signals we detect today. Studying the cosmic microwave background provides a remarkable window into the infancy of the universe. By mapping tiny variations in its temperature and density, scientists can uncover clues about the distribution of matter and energy in the early cosmos. These subtle differences are like a fingerprint of the forces that shape the universe as we know it, offering insights into the origins of galaxies, stars, and ultimately the structure of spacetime itself. The cosmic microwave background is not just a relic of the past, it is also a powerful tool for understanding spacetime on a grand scale. Detailed measurements of this radiation have revealed critical information about the universe's shape, composition, and rate of expansion. For instance, these observations have confirmed that the universe is flat on large scales and provided strong evidence for the existence of dark energy and dark matter. Furthermore, researchers use this radiation to test and refine models of cosmic inflation, a theory proposing that the universe underwent a rapid burst of expansion in its earliest fractions of a second. Each new discovery hidden in the cosmic microwave background helps to unravel the story of our universe's formation and evolution, proving it to be one of the most valuable spacetime maps at our disposal. It serves as a cosmic blueprint, encoding the echoes of creation and guiding our understanding of the universe's profound complexities. As we deepen our exploration of this ancient light, we are reminded of how even the faintest whispers of the past can illuminate the vast and intricate tapestry of spacetime. Now, as we move forward, let us venture into the concept of the observable universe and the fascinating boundaries defined by spacetime itself. Moving forward, let us turn our attention to the concept of the observable universe and the intriguing boundaries it presents. The observable universe refers to the region of the cosmos that we can see or detect from Earth, limited not by physical walls but by the very nature of spacetime itself. Light and other signals take time to travel, and because the universe has been around for roughly 13.8 billion years, we can only observe objects whose light has had enough time to reach us since the beginning of cosmic history. This distance is further stretched by the expansion of spacetime, meaning the observable universe spans approximately 93 billion light-years across. However, beyond this vast expanse lies an enigma regions of the universe that are simply beyond our view. These areas are hidden because their light has not yet had sufficient time to reach us, and due to the universe's accelerating expansion, it may never do so. This boundary is not static, it evolves with time as light from more distant objects has the chance to traverse the immense distances. Yet, as the universe expands faster than the speed of light, some regions are slipping permanently out of reach, creating a cosmic horizon that defines the limits of our knowledge. The concept of the observable universe highlights not just the vastness of the cosmos, but also the limitations imposed by spacetime itself. It is a humbling reminder that even with our most advanced tools and knowledge, there are regions of the universe that remain forever hidden. These limitations spark profound questions. What lies beyond this boundary? Are the laws of physics the same in these distant realms? Could the universe extend infinitely? Or does it loop back on itself in ways we cannot yet comprehend? As we ponder these mysteries, the observable universe serves as a stunning testament to the power and constraints of spacetime. It defines the edges of our cosmic vision and serves as a gateway to understanding the broader universe. And now, with these boundaries in mind, let us turn our gaze to yet another fascinating revelation about spacetime, the mind-bending idea known as the holographic principle. Now turning to the next astonishing concept, the holographic principle, we encounter an idea so counterintuitive, it challenges the way we perceive reality itself. Imagine for a moment that everything you see, feel, and experience within three-dimensional space, the stars in the sky, the ground beneath your feet, even your own body, might actually be encoded on a two-dimensional surface. According to the holographic principle, all the information contained within a three-dimensional volume of spacetime could theoretically be represented on its two-dimensional boundary. It is like the way a hologram on a credit card reveals a three-dimensional image from a flat surface, but on a cosmic scale. This revolutionary concept stems from attempts to unify quantum mechanics and general relativity, and gain traction through research into black hole physics. When matter falls into a black hole, it appears to vanish beyond the event horizon, the point of no return. However, physicists discovered that the information about this matter might not be lost after all. Instead, it could be stored on the black hole's two-dimensional surface area, encoded in minuscule quantum bits. This insight led to the startling realization that a similar principle might apply to the entire universe. In essence, the holographic principle suggests that our three-dimensional world is a kind of projection, much like a hologram is a projection of information stored on a flat surface. If true, this would mean the fundamental reality of the universe is encoded on a distant, two-dimensional boundary of space-time, challenging our very understanding of existence. It is a profound idea that raises questions about the nature of reality itself. Is the universe we experience just a complex illusion? Could this principle hold the key to solving some of the greatest mysteries in physics, such as the reconciliation of gravity and quantum mechanics? As we contemplate these possibilities, the holographic principle reminds us of the boundless creativity and complexity of the cosmos. It pushes the boundaries of what we thought was possible and invites us to see the universe in an entirely new way. With this mind-bending concept in place, let us now explore another cosmic revelation that ripples through space-time itself, the fascinating phenomenon of gravitational waves. Now turning to the fascinating phenomenon of gravitational waves, we delve into a cosmic revelation that has reshaped our understanding of space-time itself. Imagine space-time as a vast, flexible fabric. When massive cosmic events like the collision of two black holes occur, they create ripples that travel outward through this fabric. These ripples are what we call gravitational waves, first predicted by Albert Einstein more than 100 years ago as part of his theory of general relativity. Their existence was only confirmed in recent years. In 2015, scientists with the Laser Interferometer Gravitational Wave Observatory made history by detecting gravitational waves for the very first time. The event they observed originated from the merger of two black holes over 1 billion light-years away. The signal was faint but unmistakable, representing a momentous breakthrough in physics. It was as though we had developed a new sense, one that allowed us to hear the universe for the very first time. Gravitational waves are remarkable not only because they confirm Einstein's predictions, but also because they allow us to study cosmic phenomena in an entirely new way. Unlike light, which can be blocked or scattered by matter, gravitational waves pass through the universe largely undisturbed, carrying with them pristine information about their source. Using this new tool, observatories like LIGO and its European counterpart Virgo have since detected multiple gravitational wave events, including collisions of black holes and neutron stars. Each detection helps to unlock secrets about the most extreme environments in the universe. The study of gravitational waves also raises tantalizing possibilities for the future. Could these ripples help us understand the nature of dark matter, the mysterious substance that makes up a significant portion of the universe? Could they provide insights into the earliest moments after the Big Bang, a time when space-time itself was born? As we continue to refine our ability to detect these faint whispers from the cosmos, gravitational waves promise to deepen our understanding of the universe in ways we are only beginning to imagine. With this new lens on reality, the universe reveals itself not just as a vast expanse of stars and galaxies, but as an active, dynamic tapestry, constantly shaped and reshaped by cosmic events. Moving forward, let us explore an even more mind-bending possibility, the idea that parallel universes might exist alongside our own, hidden within the enigmatic structure of space-time. Moving forward, let's step into the captivating and speculative realm of parallel universes. Imagine for a moment that our universe, as vast and intricate as it is, could be just one of countless others, each with its own unique properties and laws of physics. This mind-bending idea stems from the concept of the multiverse, a term used to describe a theoretical collection of multiple universes existing simultaneously. But how does this possibility arise, and what does it have to do with spacetime? The foundation of this concept often comes from quantum mechanics, the branch of physics that governs the strange behaviors of particles at the smallest scales. Within quantum mechanics, there is a theory called the many worlds interpretation. This suggests that every time a quantum event occurs, like an atom's particle choosing one state over another, the universe essentially splits, creating a new reality where each possibility plays out. While this idea may sound like science fiction, it is grounded in serious scientific debate and mathematical exploration. Spacetime itself, the fabric of our universe, plays a crucial role in multiverse theories. Some scientists propose that our universe might be just a bubble floating within a vast sea of other universes, each bubble representing its own distinct spacetime. This idea often arises when studying cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. If inflation happens repeatedly in different regions, it could create multiple separate universes, each isolated from the others. Parallel universes also emerge in string theory, a leading candidate for a theory of everything. This framework suggests the existence of extra dimensions beyond the familiar three of space and one of time. These hidden dimensions could harbor other universes entirely separate from our own. While we currently lack direct evidence of parallel universes, certain patterns in cosmic background radiation or anomalies in particle physics might one day hint at their existence. The implications of parallel universes are as profound as they are humbling. Could there be another version of you living a completely different life in an alternate universe? Could universes with entirely different physical laws exist, possibly harboring life forms unimaginable to us? While we are only beginning to scratch the surface of these questions, the study of spacetime provides the framework to explore these extraordinary possibilities. As we grapple with these questions, one thing becomes clear: the universe, whether singular or part of a multiverse, is far stranger and more wondrous than we ever imagined. Now, let us take a step back from this speculative frontier and explore a question closer to home. Why does time move forward and not backward? What defines the arrow of time within the vast fabric of spacetime? Now, turning to the fascinating concept of the arrow of time, let us uncover why time seems to flow in one direction forward but never backward. At the heart of this mystery lies a fundamental principle of physics, the second law of thermodynamics. This law states that in any closed system, entropy, which can be thought of as the measure of disorder or randomness, tends to increase over time. In simpler terms, things naturally progress from order to chaos, not the other way around. For example, imagine breaking an egg. Once the shell is shattered, the contents spill out and the egg becomes more disordered. You will never see the reverse happen, a broken egg spontaneously reassembling itself into a perfect one. This irreversible increase in entropy is what gives us the perception of time moving forward. But why does the universe itself follow this rule? To understand this, we need to look back at the early moments of existence. At the time of the Big Bang, the universe began in an incredibly low entropy, highly ordered state. As the universe expanded and evolved, entropy increased, giving rise to the arrow of time that we experience. The flow of time is essentially a reflection of this cosmic journey from order toward greater disorder. Interestingly, this connection between entropy and time also explains why we remember the past but not the future. Our brains, like the universe, operate in a way that relies on processing and storing information in an ordered sequence, which aligns with the forward progression of time. However, some aspects of physics challenge this one-way perspective of time. The fundamental laws governing particles at the quantum level are oftentimes symmetric, meaning they work the same way whether time moves forward or backward. Yet, on the scale of everyday life and the wider universe, the increase in entropy dominates, giving time its directional flow. This duality, a timeless symmetry at the smallest scales versus the forward arrow we observe in our daily lives, remains one of the deepest puzzles in modern science. The arrow of time also raises profound philosophical questions. Is the future already predetermined, or does it unfold in a way that depends on the choices we make? Could there be regions of the universe, or even other universes, where time flows in reverse, where entropy decreases rather than increases? While these ideas remain speculative, they highlight how spacetime continues to challenge our understanding of reality. And yet, as we contemplate the relentless forward march of time, another mystery beckons. What if time and space themselves, as smooth and continuous as they seem, are not as stable as we imagine when viewed on the smallest scales? What does the fabric of spacetime look like when we zoom into its most fundamental building blocks? Let us now explore the quantum-level nature of spacetime and the surprising possibilities it reveals. Now turning to the quantum realm, we uncover a groundbreaking perspective. Spacetime, which appears smooth and continuous in our everyday experience, might actually be anything but. When viewed at the smallest imaginable scales, known as the Planck scale, spacetime is theorized to be far from uniform. Instead, it may resemble a frothy, ever-changing sea of energy, a concept often referred to as spacetime foam. This idea stems from quantum gravity theories, which attempt to combine quantum mechanics with Einstein's theory of relativity. To picture this, imagine the surface of a calm ocean from afar. It looks flat and smooth, much like how spacetime seems to us on larger scales. But if you zoom in close enough, you would see waves, ripples, and turbulence that disrupt its apparent smoothness. Similarly, at the quantum level, spacetime could be a dynamic, fluctuating fabric rather than a perfectly stable backdrop. These tiny fluctuations might be caused by the constant creation and annihilation of virtual particles, quantum phenomena predicted by the uncertainty principle. Interestingly, this foamy nature could help explain some of the universe's most enduring mysteries. For instance, it might offer insights into what happens at the edge of a black hole, or the very beginning of the universe when spacetime itself was unimaginably compressed. Some theories even suggest that this quantum foam could hold the key to unifying the forces of nature, revealing a deeper framework that underpins everything we know about physics. While this concept is still speculative, scientists are developing innovative ways to test these ideas. Future experiments involving high-energy particle physics or cutting-edge gravitational wave detectors might provide evidence of spacetime's granular structure. If proven, this discovery would fundamentally reshape our understanding of the universe, showing us that the very fabric of reality is far more complex and dynamic than we ever thought possible. And as we ponder this intricate and unpredictable terrain, we are led to yet another astonishing idea. What happens when spacetime itself begins to ripple under extreme cosmic events? Let us now delve into the phenomenon of gravitational waves and the secrets they reveal about the universe. Now turning to one of the most profound puzzles in modern physics, we encounter the black hole information paradox, a mystery that challenges our very understanding of spacetime and quantum mechanics. At its core, this paradox revolves around the question of what happens to information when it falls into a black hole. Information, in this sense, refers to the fundamental details about the physical state of particles, such as their position, energy, and momentum. According to quantum mechanics, information cannot simply vanish. It must always be preserved in some form. Yet, black holes, with their immense gravitational pull and the inescapable event horizon, appear to defy this principle. When anything crosses the event horizon, it is believed to be irretrievably lost to the outside universe, as black holes eventually evaporate through a process known as Hawking radiation. Named after the renowned physicist Stephen Hawking, they emit particles that seem completely random and unconnected to whatever originally fell into them. This leads to a perplexing contradiction. If the information about the fallen matter is wiped out, it would violate a key tenet of quantum mechanics, potentially undermining the very framework of physics as we know it. To resolve this, scientists have proposed several intriguing ideas. One such suggestion is the concept of holography, which posits that the information swallowed by a black hole might not be lost at all. Instead, it could be encoded on the event horizon itself, much like a three-dimensional object projecting its image onto a two-dimensional surface. Another proposal involves quantum entanglement, where the tiny particles emitted as Hawking radiation could be connected in ways that preserve the original information, albeit in an incredibly scrambled form. Some theories even suggest that black holes might act as portals to other regions of spacetime, where the information could continue to exist in ways we cannot yet comprehend. While none of these ideas have been conclusively proven, they offer tantalizing hints at a deeper, unified framework that could bridge the gap between quantum mechanics and Einstein's theory of relativity. This paradox has captivated the brightest minds in physics and spurred groundbreaking research into the nature of spacetime. Efforts to solve it may not only unlock the secrets of black holes, but also reshape our understanding of the universe itself, revealing insights into the most fundamental fabric of reality. And as we marvel at this cosmic enigma, it beckons us to consider an even grander question. What could the latest efforts in theoretical physics reveal about resolving this paradox and the nature of spacetime altogether? Now turning to the latest research on the black hole information paradox, scientists are delving deeper into theories that might bridge the divide between quantum mechanics and general relativity. String theory, a leading candidate for a unified theory of everything, offers a particularly fascinating perspective. According to string theory, the fundamental building blocks of reality are not particles but incredibly tiny, vibrating strings of energy. These strings could potentially hold the key to understanding how information behaves in the presence of a black hole. Some researchers propose that string theory's framework may reveal hidden mechanisms that preserve information, even as objects are pulled into a black hole and seemingly lost forever. Alongside string theory, the concept of quantum entanglement has become a cornerstone in exploring this paradox. Quantum entanglement occurs when particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of distance. Scientists are investigating whether the particles emitted as Hawking radiation could maintain entanglement with the particles that initially fell into the black hole. If true, this could provide a pathway for the information to remain intact, albeit in an extraordinarily complex and scrambled state. Adding to this, advancements in the study of firewalls, a proposed phenomenon at the event horizon, have stirred intense debate. Some theories suggest that these firewalls might prevent the complete destruction of information by acting as a barrier where quantum information is stored or transformed. Others argue against their existence, pointing instead to more subtle mechanisms within spacetime's quantum structure that could safeguard information. Furthermore, recent developments in the concept of holography, particularly the AD/CFT correspondence, have opened up new possibilities. This idea suggests that a black hole's three-dimensional interior could have an equivalent description on a two-dimensional boundary. Researchers are exploring whether this duality could resolve the paradox by showing how information is preserved and ultimately retrievable, even if it appears inaccessible from our perspective. While these theories remain speculative, they represent cutting-edge efforts to tackle one of physics' most profound mysteries. Resolving the black hole information paradox could not only illuminate the nature of spacetime, but also guide us toward a deeper theory that unifies the laws of the quantum world with the cosmic scales of general relativity. As research progresses, each breakthrough brings us closer to unraveling the enigma of black holes and understanding the true essence of the universe. And as we ponder these advances, it becomes clear that the quest to decode this paradox is not merely about black holes, but about redefining what we know about reality itself. As the next phase of the journey into spacetime unfolds, we step into one of the most mind-bending questions in cosmology: what came before the Big Bang? The conventional understanding tells us that time and space themselves began with the Big Bang roughly 13.8 billion years ago. This leaves us in a conundrum because without time, the idea of a before becomes meaningless. However, scientists have proposed several fascinating hypotheses to tackle this perplexing question. One such idea is the cyclical universe model, which suggests that the Big Bang might not have been the absolute beginning, but rather just one phase in an endless cycle of cosmic birth, expansion, and contraction. According to this theory, the universe could undergo repeated cycles where it collapses into a big crunch before rebounding into a new Big Bang, creating an infinite loop of universes. On another front, quantum gravity theories attempt to address the origin of the universe by merging quantum mechanics with general relativity. These theories suggest that at extremely high energy conditions, like those present during the Big Bang, the classical notion of spacetime breaks down and is replaced by a different probabilistic framework. For instance, some models propose that spacetime might have emerged from a more fundamental quantum state where the concepts of before and after do not apply in the traditional sense. Perhaps even more intriguingly, some researchers speculate about a pre-Big Bang state where our universe might have been connected to another universe or dimension. In this perspective, the Big Bang could be seen as a transition between two distinct phases of reality, with one universe giving rise to another in ways we are only beginning to explore. Though we may never gain a definitive answer, these theories illuminate the possibilities of what could lie beyond the boundaries of our current understanding. Exploring what might have preceded the Big Bang isn't just about looking back in time. It's a step toward unraveling the deepest truths about the nature of existence itself. Moving forward, let us dive deeper into the extreme spacetime distortions caused by neutron stars, truly cosmic marvels of density and gravity. These are objects so compact that they squeeze more mass than our Sun into a sphere roughly the size of a city. Such immense concentration of matter creates gravitational fields that distort spacetime in truly dramatic ways, offering scientists a unique opportunity to study the very fabric of the universe. These distortions not only affect nearby objects but also bend light itself, causing phenomena like gravitational lensing, where light from background stars is bent around the neutron star, creating a magnified or distorted image. But the wonders of neutron stars don't stop there. They are also known for their incredible rotational speeds, with some spinning hundreds of times per second. These rapidly spinning neutron stars are observed as pulsars, emitting beams of electromagnetic radiation that sweep across space like the beams of a lighthouse. This makes pulsars invaluable tools for probing the laws of physics under extreme conditions. Neutron stars also exhibit extraordinary behaviors like X-ray bursts, which occur when matter from a companion star accumulates on the neutron star's surface, igniting powerful nuclear reactions. These bursts release astonishing amounts of energy in just seconds, temporarily outshining entire galaxies in the X-ray spectrum. Such phenomena make neutron stars not just remnants of stellar deaths but dynamic laboratories where scientists test theories of gravity, nuclear physics, and quantum mechanics in ways that are impossible to replicate on Earth. Additionally, studying neutron stars helps us understand the boundary between different types of matter. Researchers believe that inside these stars, matter might be compressed to such extraordinary levels that it forms exotic states like quark matter, a phase of matter never observed directly. This could offer clues to the very building blocks of existence, pushing the limits of our understanding of space-time and the fundamental forces of nature. As we uncover the secrets of neutron stars, we find that they are not just cosmic relics but dynamic, fascinating engines of discovery that expand our knowledge of the universe. And as we turn our attention to their close relatives, black holes, and their unique interaction with spacetime, even more astonishing revelations await. With the next phase of the journey in sight, let us explore the cosmic microwave background, often referred to as the faint afterglow of the Big Bang. This relic radiation, spread throughout the universe, provides an extraordinary map of spacetime as it was nearly 14 billion years ago, just a few 100,000 years after the universe began. However, this ancient light is not uniform. Subtle variations, known as anisotropies, appear as tiny fluctuations in temperature across the sky. While these variations may seem minor, they hold profound implications for our understanding of the cosmos and even the possibility of a multiverse. Scientists have long studied these temperature fluctuations to better understand the distribution of matter and energy in the early universe. Intriguingly, some irregularities in the cosmic microwave background defy conventional explanations. These anomalies, such as the so-called cold spot, have sparked speculation that they could be the result of gravitational interactions between our universe and other potential universes. Imagine spacetime itself as a vast, interconnected landscape. Could these peculiar patterns be the fingerprints of neighboring universes colliding or subtly influencing our own? This idea is at the frontier of cosmology, where theories like eternal inflation propose that our universe might be just one of many within a far greater multiverse. In this scenario, universes bubble into existence, potentially interacting in ways that leave traces in the cosmic microwave background. If such interactions are confirmed, they could revolutionize our understanding of reality, suggesting that spacetime is not just the stage for our universe but part of a much broader and more complex existence. Still, these hypotheses are far from settled, and researchers continue to investigate whether these anomalies can be attributed to mundane explanations like data processing errors, or if they truly hint at something extraordinary. Regardless, the cosmic microwave background remains one of the best tools for probing the deepest questions about spacetime, offering us a window into the very origins of the universe and possibly beyond. With these tantalizing prospects, our journey into spacetime only grows more intriguing as we next explore the concept of the observable universe's boundary and what lies beyond our cosmic horizon. With the next phase of the journey in sight, we delve into the mysterious realm of spacetime at the Planck scale, where the fabric of the universe is thought to become unimaginably intricate. Here, at scales smaller than a billionth of an atom, the conventional rules of physics cease to apply, and spacetime itself is believed to be anything but smooth. Instead, it is theorized to resemble a quantum foam, a frothy, ever-changing sea of tiny fluctuations. This is the domain where quantum mechanics and general relativity collide, challenging our deepest understanding of reality. To unravel the mysteries of this extreme scale, scientists turn to groundbreaking theories like loop quantum gravity and string theory. Loop quantum gravity suggests that spacetime is not continuous but instead consists of discrete, tiny loops woven together into a network. Imagine a fine mesh-like structure where each loop represents a building block of spacetime itself. This idea radically redefines how we think about space and time, proposing that they emerge from more fundamental, microscopic processes. On the other hand, string theory offers a different perspective, proposing that every particle and force is made up of one-dimensional vibrating strings. These strings are so unimaginably small that they could form the very threads of spacetime at the Planck scale. String theory also introduces the idea of extra dimensions of space, hidden within these minuscule scales, which could provide a deeper framework for understanding how spacetime operates. Despite their differences, both loop quantum gravity and string theory attempt to bridge the gap between the principles of quantum mechanics, which govern the smallest scales, and general relativity, which describes the largest. Together, these theories aim to unlock the secrets of quantum gravity, the missing piece needed to fully comprehend spacetime in all its complexity. While direct experimental evidence for these theories remains elusive, researchers are devising creative methods to test their predictions. For instance, scientists are investigating whether tiny fluctuations in spacetime might leave subtle imprints on light traveling across the cosmos, or exploring high-energy phenomena like black hole collisions for clues about quantum gravity. As we push the boundaries of our understanding, the Planck scale represents a frontier where the very nature of spacetime, and perhaps even the universe itself, awaits discovery. With these profound questions in mind, we now turn our gaze to the arrow of time, unraveling why time appears to flow in one direction and what that means for spacetime as a whole. With the next phase of the journey in sight, we bring our exploration of spacetime to a close by reflecting on the awe-inspiring discoveries and ideas we have uncovered. From the curving of spacetime by gravity and the enigmatic nature of black holes to the mysterious quantum foam at the Planck scale, each fact has offered a glimpse into the profound complexity of the universe. We've traversed theories of wormholes, the expansion of spacetime, and the notion of time itself beginning with the Big Bang. We've pondered the potential for time travel, the ripple effects of gravitational waves, and even the possibility of parallel universes hidden within the multiverse. These astonishing ideas have reshaped our understanding of reality, challenging us to think beyond the boundaries of everyday experience. Spacetime is not merely a backdrop for the events of the cosmos, but an active, dynamic fabric that connects everything within the universe. As humanity continues to push the limits of science, uncovering new clues and testing bold theories, the mysteries of spacetime remain a wellspring of wonder and inspiration. Which of these incredible facts about spacetime captivated you the most? Share your thoughts in the comments below. We'd love to hear your perspective. And if you enjoyed this journey through the cosmos, do not forget to like the video, hit that subscribe button, and turn on notifications for more fascinating content about the mysteries of space. Until next time, keep looking up and letting the universe fill you with wonder.